discussion and of statistical models, and then do sort of like a summary of what we've gone over the last 2 weeks. So I want to talk today about logistic regression, and just to remind you what we talked about yesterday and to some degree last week was linear regression, or the general linear model, where the dependent variable or the outcome variable is continuous, and it's assumed that it's normally distributed, although that can be that assumption can be violated to some degree, and will still be okay, even if it's not actually normally distributed. But anyway, the regression equation is our outcome variable is a function of our dependent or our independent or predictor variables, and in this case the regression coefficients, the B1, B2, and so on, represent the change in the outcome variable for every unit change in the independent variable. And we talked about in linear regression, particularly in looking at predictive models, that the R squared is really our important statistic to look at because it represents the proportion of variance in the dependent variable that's accounted for by the independent variable or variables. So the difference when we have logistic regression is that our outcome is dichotomous. So, you know, for example, dead, alive, positive, negative, yes, no. And this is referred to as the generalized linear model. There are some other things that come under the heading of generalized linear models, but the one that you would most often see or probably do in a research project is logistic regression, where we have a dichotomous variable. And so now our dependent variable is actually the log, what we call the log odds or the logit. So the odds of an outcome, of course, is the probability of that outcome divided by 1 minus the probability of that outcome. And so in our regression now, we're going to look at the log of the odds. And so the change in log odds of an event's, it represents the change in the log odds of an event with 1 unit change, either increase or decrease in our independent variable. And it can be increasing or decreasing. So our in our ordinary linear regression, we looked at the normal curve. Here for logistic regression is our logistic distribution, our logistic regression curve. And you might say that, well, that doesn't look very linear to me. Well, that's true at the extremes, but through the middle, it's quite linear. And so in looking at the distribution here, you can tell that if our probability of an outcome is very small, getting near 0, or our outcome occurs almost all the time in our sample or in our population, that we might be in trouble trying to model it as with logistic regression. But for the most part, we're going to find that the probability of whatever outcome we're interested in is sort of more in the middle, where the probabilities are linear with the independent variables. So the way that we interpret the results from a logistic regression is it's similar to linear regression that basically the regression coefficients are slopes. They indicate the rate of change in the log odds of the event as the independent variable changes. And so the way that we look at logistic regression is not so much in terms of the actual regression coefficients, the betas, but what is more understandable is look to the change in the probability of the event as the independent variable changes. And so at the bottom there, I have how you find the probability of an event given the independent variable x, is that we exponentiate the regression equation alpha plus beta x, and then we divide by 1 plus the exponentiated regression equation. And so that gives us the probability of the event that we're interested in. And then what we primarily do then is we look at the probabilities in terms of the independent variables. And this is particularly helpful if we have multi-variable logistic regression with just one variable in the model. It's fairly straightforward whether we look at the regression coefficient or the probability. So the way we interpret this is just similar to regular linear regression, that the sign of the regression coefficient can be either positive or negative. And so that indicates that the log odds of y is increasing if it's positive, or if the regression coefficient is negative, decreasing for every 1 unit increase in the predictor or the independent variable. And so if our regression coefficient is greater than 0, then that indicates an increase in the log odds. And if it's less than 0, then it's a decrease in the log odds. And then just the same as in regular linear regression, if from our, doing our statistical test, if it turns out that the regression coefficient is equal to 0 or statistically equal to 0, then that means there's no linear relationship between the log odds and the independent or predictor variables. Now, one of the differences also in logistic regression, that is, if we exponentiate the regression coefficient, then what we get is what's called an odds ratio. And so I have an example here that I'm going to go through to illustrate this, and this is data that William has for one of your exercises as far as doing logistic regression. So here we have cardiovascular disease, yes or no, and we want to look at that as a function of age. So here are dependent variable cardiovascular disease we code as is a yes or no variable. So we code that as 1 equals yes and 0 equals no. And we can, because it's dichotomous variable, we can code it with any number we want, but there's an advantage to coding dichotomous variables as 1 or 0 because it really aids interpretation. So in this case, 1 equals yes and 0 equals no. And so we have our output here when we do our logistic regression analysis is similar to what we see from the regular linear regression. We have we have our regression coefficient for our independent variable, and then we have a constant. And then you see that similar to linear regression, we have a confidence interval, a 95% confidence interval. And so and then we have our p-value as to whether this is statistically significant or not. And what we mean by that, in this case, with just the regular regression coefficient, is this coefficient 0? And so we see that it's not, and then we have a p-value associated with that. And you notice that part of the output has what's called a pseudo R squared. And so that's analogous to the R squared in ordinary linear regression, but it's not calculated the same way. And usually this isn't interpreted because you can't, it doesn't mean the same thing as it does in linear regression. And so if we wanted to get the probability of cardiovascular disease as a function of age, then we would just exponentiate our regression equation, minus 5.2 here plus 0.09 times a particular age, and then we would divide that by 1 plus the exponentiated regression equation. And so that would give us the probability of cardiovascular disease at whatever age we put in our equation here. And so we can get a range of probabilities by age by just solving this equation. If we, as I mentioned, exponentiate the regression coefficient, then we get an odds ratio. And so in this case, we see that the exponentiated value in the previous slide equals 1.10. Okay, so how do we interpret this? Well, you see the p-value is still the same, but our confidence interval now is expressed as an odds ratio. And so now what is important to understand is that our confidence interval now, if it's significant, statistically significant, will not include 1. Because if we're comparing, say we're comparing two groups, then that means that the odds of for either group is the same. It's the odds of one divided by the odds of the other. And so if they're equal, that the odds ratio will equal 1. And so what this means is that if the odds ratio here was 1, or our confidence interval included 1, then that would mean that the odds of cardiovascular disease was the same regardless of what age a person was. But in this case, we see that it's not, from a statistical standpoint anyway. So how do we interpret this? Well, interpreting the odds ratio is actually do this a couple ways. So what this means is that for every 1 year increase in age, the odds of cardiovascular disease increases by a factor of 1.1. Or another way of saying this is that for every 1 year increase in age, there's a 10% increase in the odds of cardiovascular disease. And so the 10% comes from just subtracting the odds ratio, or subtracting 1, and you get 10%. That's the other way of expressing what the odds ratio means. Now, if the odds ratio is less than 1, then that means that the percent increase is actually 1 minus whatever the odds ratio is. So example, if the odds ratio here was 0.98, then our interpretation would be for every 1 year increase in age, there's a decrease in the odds of cardiovascular disease by 2, or by 9%. Yeah. So how the odds ratios is interpreted is a bit different from our linear regression coefficient. So we can calculate an odds ratio from a 2x2 table of events. And so last time or maybe last week, we looked at calculating the p-value of a 2x2 table or any size of table. But if we have a 2x2 table where the rows are groups that we're looking at. So for example, if we have an intervention versus control group, and then we have the number of events in our first column here and the non-events in our second column here, then we can calculate the odds ratio from this. In other words, the odds of having an event in the intervention group compared to the control group. So that's just this calculation, although it looks kind of complicated here, is really straightforward. It's basically the odds of an event in the intervention group. So that's 46 divided by 100. And then that's divided by 1 minus the number of events by 100, or that's the same thing as 54 divided by 100. But in other words, this is the odds of an event versus the odds, or 1 minus the odds of that. And then so for the control group, it's just the same thing. It's 37 divided by 100 divided by 1 minus 37 divided by 100. And you take that ratio there and you get the odds ratio. And it turns out for this table, the odds ratio is 1.45. So that means that the odds of experiencing the event in the intervention group is greater in the intervention group than the control group by a factor of about 1.5. Now there's a shortcut for calculating the odds ratios in a 2x2 table, and it's basically taking the ratio of the cross products here. So if you take 46 times 63 and divide that by 37 times 54, you get the odds ratio of 1.45. So in this, I've shown you how to calculate an odds ratio from a 2x2 table. And so in terms of the interpretation here, then so we would say that the event is nearly 1.5 times more likely to occur in the intervention group. And so statistical significance here is then whether the odds ratio, the confidence interval includes 1 or not, or is the odds ratio statistically different from 1. And we can obtain that by just doing a chi-square test like we did earlier in calculating the p-value for this. So one of the assignments that you have is to calculate the p-value and the 95% confidence interval of this odds ratio for this table. So we can then extend the logistic regression here, just as we did linear regression, to more than one independent variable. And these independent variables, the x's here, can be dichotomous. They can be continuous, ordinal, or any kind of numeric value here. But you can see that what we're modeling is the log odds, the log of the probability of the event divided by 1 minus the probability of the event. And so the interpretation is just the same as we looked at before with the simple one predictor variable is that we have an increase in the log odds for 1 unit increase in the independent variables, and the as just as in linear regression, the regression coefficient is adjusted for all the other regression coefficients or all the other variables that are in the model. Okay, so I want to show you just an example here of the output from a particular study we did some time ago, and the odds ratios, the interpretation of the odds ratios. And so this is looking at PCI, percutaneous coronary intervention or stenting patients, and then looking at their whether they were readmitted within 30 days. So the outcome here is just readmission within 30 days, yes or no. And so, for example, we have age, which in this case I expressed in 10-year units. So I think they were probably decades, so like 20 to 29, 30 to 39, and so on. So what the odds ratio means here of 1.25 is that for every 10 years increase in age, the odds of being readmitted within 30 days is 1.25 times greater than for every 10 years increase in age. Or as we mentioned before, there's a 25% increase in the odds of being readmitted within 30 days for every 10 years increase in age. And so you can see here that we have the 95% confidence interval, which does not include 1. And so we have actually a very small p-value here. And then we have sex in our model as well. And so we've set this up so that we're comparing the odds for females versus the odds of males. And so what this means is that females are about 1.2 times more likely to have or to be readmitted within 30 days than males, or they have the odds are 18% greater for females than for males. And although at least at the 0.05 level, this is not statistically significant, but it's probably close enough to consider. Then I want to just go over another variable here that's included in the model, and that's race. And now we have 3 categories of race: white, black, and other. And so when you have more than 2 categories, well, actually with 2 categories, one of them has to be the reference category. And so when we had female versus male, the male was the reference category. And now we're going to, in our 3 category variable here, we're going to have white as the reference category. And so the odds ratio for white is just 1. And then so the comparison of the other racial groups is in reference to white. And so our meaning here, our interpretation here is that blacks have are 1.3 times more likely to be readmitted within 30 days than whites. Okay. And then the other category here, although it's not statistically significant, but what this would mean is that in relationship to whites, the other races are 2% less likely to be readmitted within 30 days than whites. So the other odds ratios here are always in comparison to the reference category. Now we can test whether blacks are different from from other races in this case, but this is not what these odds ratios mean. They're the comparison between this odds ratio and this odds ratio. You have to do another test. So that's important to remember, that when you have multiple categories here, that the odds ratio is always in reference to the reference category. And then so one other here that I'll take time to go over is whether the PCI was elective or not elective. And so our odds ratio here is 0.59, about 0.6. So that means that the those that have an elective PCI are less likely to be readmitted within 30 days by a factor of 0.4, or 1 minus 0.6, or that they're 40% less likely to be readmitted within 30 days. And so then the rest of the variables here interpreted in the same way. And so being transferred from another hospital, also the odds ratio is less than 1. So this means that those that have been transferred are less likely to be readmitted in 30 days by a factor of 0.5, or about 50% less likely to be readmitted within 30 days, kind of depending on what's, I guess, more meaningful or easier to interpret. When we look at a logistic regression model, when we looked at the linear regression model, one of our important variables we wanted to look at is the R squared. In logistic regression, we want to look at the measure of discrimination. This is referred to as the C index. And the C index, our measure of discrimination, will range, when we calculate, will range from 0.5 to 1. 0.5 being there no discrimination. In other words, based on your model, you can't tell whether they're going to be positive or negative for the event, or yes or no for the event. 1 indicates perfect discrimination. That is, you can always discriminate between groups, or in relationship to continuous variable and the particular values of that variable. So in this case, we have a C index of about 0.76, so that's not too bad. It tells us that we have pretty good discrimination in terms of being readmitted within 30 days based on this particular model. So in terms of the discrimination, or the C index, as I mentioned, a value of 0.5 means there's no discrimination. Generally, if we get an index of 0.8 or greater, we got really good discrimination. 0.6 to 0.7 is really mediocre. 0.6 isn't that much different from 0.5 in terms of discrimination. So you might see some folks calling, or researchers calling, 0.65 really good discrimination. Well, not really, but as it depends on how you want to present your results. The other thing that we need to look at in relationship to how well our model predicts is what's called calibration. And by calibration, we mean, do the predicted probabilities equal the observed probabilities of the event? And so obviously, we want them to be a good fit. That is, that the predicted probabilities are pretty much equal to the observed probabilities. And so what we do is we make a plot of the observed probabilities with the predicted probabilities. And then we calibrate a slope of the relationship here. And so obviously if the slope is 1, that means there's a perfect perfect correlation or perfect lineup of the predicted and observed probabilities. In other words, they all fall along the same line. If it's not 1, then it sort of depends on how close it is to 1, whether we have good calibration or not. And so in the model that I just looked at in terms of 30-day readmission, I plotted here the observed proportion, and then typically what you do is calculate quintiles, or more likely deciles, 10 units of the predicted probability of readmission, and see how they relate. And so you can see that doing this with just quintiles in a bar graph here, that I have pretty good discrimination in that as the observed probabilities increase, so do the predicted probabilities. And then the other way of showing this or describing this is in terms of just a regular regression line. And so my dotted line here would be ideal calibration, where I'd have a slope of 1, and then I plot my observed probabilities and predicted probabilities and see how well that lines up with my ideal line. And so in this case, you can see it's obviously not perfect, but turns out that the slope is 0.97. So I have pretty good calibration here in terms of the observed probabilities being similar to the predicted probabilities. So if my calculated calibration slope is really different, say in other words, it was, more or less in line with the ideal slope, then the slope here would be something quite different from 1. Okay, so what I wanted to do then is I wanted to take some time here to go over a study to illustrate some of the concepts of logistic regression. And I wanted to do this in the context of, I guess, showing how in what the investigators did here turns out to be not really correct as far as their research question is concerned. And so what they're looking at here is percutaneous repair, surgical repair versus medical treatment for mitral regurgitation. So we have 2 groups, and the intervention group that receives the medical therapy plus the surgery, and then the control group receives just the medical therapy. So what they are looking at here in terms of, if we were to, and they do state this in terms of a logistic regression issue, they would be looking at the outcome of being yes or no. And in this case, their outcome is either death or an unplanned hospitalization for heart failure at 12 months. So I've sort of highlighted their statement here of their research question, and basically, as I just said, they are looking at the 2 groups, and their outcome variable is a 1 or 0, and you get a 1 if you have either heart failure or you have hospitalization. So that's what we call a composite outcome. So they describe then their methods and their patients and their randomization to each group. And so this is just a statement of their outcome of either death or unplanned hospitalization at 12 months. And then as far as their statistics go, their first thing that they do here is they calculate how many patients they're going to need. And so to do that, you have to come up with what you think is a reasonable effect size. And so this, in other words, what's the expected difference that you might see between the two groups? And so to do this, they look in the literature. There's different ways you can do this. You can do a pilot study or look in other studies that have been done. And so they find that one study found that with the patients that just received the medical therapy, that their the outcome is as high as 50%. And so in another registry of heart failure patients, they found that at 12 months, the rate was about 33%. So this is the difference, 50% versus 33% that they want to, excuse me, that they want to be able to demonstrate. So it's a 17% difference. And so they determined that 144 patients in each group would give them sufficient power to show that income or to demonstrate that that difference. And so they used a chi-square test to just compare the difference between 50% and 33%, and what the power would be with 144 patients. And there's a way of doing that. And then they're assuming that there's going to be a 10% loss to follow up. So they're actually going to enroll more than 144 in each group to compensate for their loss to follow up. And then so their statistics that they're going to do, they say that they're going to do their analysis by the intention to treat principle. And so what is meant by that is that if patients who are randomized to one group, they're going to be treated as if they got that intervention, even if they didn't. So that's what is meant by intention to treat. Sometimes it's possible that they can do an analysis of what patients actually received, but that's really a secondary analysis. Most randomized trials do the intention to treat analysis. But anyway, what they're using here is a logistic regression to estimate the odds. And they did an adjustment for the fact that they had different centers. In other words, patients came from different centers, but basically they wanted to look at the odds of the outcome between the two groups. So they're comparing the odds of death or hospitalization in each group. Okay, and then in addition, because they're looking at a 12-month period here, they're going to do Kaplan-Meier survival curves, which we talked about briefly last week, the first week, and compare the survival over a 12-month period with between the two groups. So they say that so it's a two-sided p-value of less than 0.05 was considered to be statistically significant. And then interestingly here, for the secondary outcomes, they're not going to do any significance testing because they say that they're making no adjustment for what is known as multiplicity, which I'll describe in the next hour. But the reason they're not doing that is because a lot of the data that they are gathering, like functional status, quality of life, were missing. So they are not going to do those analyses. So their primary outcome they're looking at here is either death or rehospitalization. So they report the results here. They give the proportion in each group that either died or was hospitalized. And so they find that 83 patients in the intervention group and 78 patients in the control group were died or were hospitalized. So you get an odds ratio of 1.16. And the confidence interval is 0.73 to 1.84, which is not statistically significant. So interestingly, what they found was that the control group actually did better. And so their odds ratios here of 1.16, because remember, they're comparing the intervention group to the control. So this would be interpreted as the intervention group odds in relationship to the control group odds. So this means that the intervention group odds of dying or being hospitalized is 16% greater than the control group. So they actually, in terms of the odds ratio, what they found, or the percentage of what they found, the control group is actually doing better. So obviously their hypothesis wasn't, they couldn't reject they couldn't reject the null hypothesis, which was sort of a kind of interesting finding. And so then basically what you have to do in the rest of your paper is discuss why you think that happened. And so here's the table of their primary outcome, the odds ratio in this case of 1.16. I had the intervention group done better, then this odds ratio would have been less than 1 and might have been statistically significant, but we don't know that. And then because they wanted to look at the survival over 12 months, then they had they did their survival comparison of the two groups and found that there was essentially no difference between the two. And you can see the control group here versus the intervention group, that it's fairly, they're fairly similar. So in terms of their write-up of their results, they say that that in conclusion, that the intervention group, the difference between the intervention group and the control group for heart failure at 12 months did not differ significantly. Well, that's kind of a I guess, how can I say it? That's kind of a non-conclusion. Because it sort of implies that because they didn't differ significantly, that you know, that's what the finding is, and from a statistical standpoint, that's true. They didn't differ significantly, but in writing up your results, that's not what you really want to focus on. So in my typical sarcastic kind of way, I wrote some different conclusions of how it should have been written up, that what they needed to say is that we found no evidence of a difference between the intervention and control group. And they actually overestimated the effect size, which is really quite large, the 17% difference. And so they were really underpowered to detect any realistic difference. And then, of course, the results turned out in the wrong direction. So that was probably unexpected. And then in terms of their determining their sample size, they actually powered on the wrong statistical test. Now, they're determining their sample size for the logistic regression. I mean, that's okay, you can do that, but what they really should have powered on was their survival comparison of the survival curves over 12 months. And the reason for that is that the comparison of survival curves will take more patients, more individuals in your study to demonstrate statistical significance. So anyway, I found this kind of an interesting study, that the statistics were quite straightforward, and they did a pretty good job of reporting those, but and I suppose because they didn't find any statistical difference, there wasn't much to say. But there are some things they could have done differently or written differently. So anyway, that gives you kind of an idea of how statistics are presented in published papers, and just understanding what they're doing, and then do the conclusions follow their results. It's important to understand what their research question is, what they're doing to show that or demonstrate that, and then what they conclude about it. So one other thing that I want to point out about logistic regression is, if you do logistic regression yourself, or you're reading research studies, one of the things that you want to look for and be suspicious of is extreme values. And so by that, I mean either odds ratios that are really large, unusually large, or lower and upper confidence intervals here that are really either really large or really small. And so you can see I have some examples here where the comparison of race here, that for the other race we have an extremely small odds ratio, virtually zero. So that tells you, and then we have the same thing for whether or not they're on Medicaid, and then their insurance. So if you see things like this, where either the odds ratio itself or either the upper or lower bounds of the confidence intervals are really, really small, you know that something is really amiss. And probably what this means in this case, when it's really, really small, means that there's hardly any patients or any subjects in your study in that particular category. So in either doing logistic regression or reading about it, you want to sort of look for those kinds of things where you have really either really wide confidence intervals, like here for female, it's the upper bound is 292, which is pretty unreasonable. And then the lower bound is like 1.8. And so you can see the extremely wide confidence interval here. So just be aware of that, be suspicious of those kind of results. So just to sum up, if you have continuous variables and you want to make categories out of them, that helps in interpretation, but know that it decreases the power of your study. And then if the relationship between your outcome and any continuous variables is actually nonlinear, then you can't really interpret the odds ratios as you normally would, because remember, this is looking at linear relationships. And then to look at model discrimination and calibration, and those should be reported in a study, but oftentimes they're not. And then if we have more than 2 categories in our outcome, we can do what's called ordinal logistic regression, or if they're just categories without an order to them, we can do multinomial logistic regression. So with that, I'll stop. And I guess, John, if we want to take a 10-minute break, and then I'll finish up with sort of a summary of what we've covered over the last 2 weeks.
Yeah, so I think John will be, John might not be reachable now. So yeah, so we'll do that, and then we'll get back and continue. So it's currently for 3 minutes.
Yeah, 10 minutes break is fine. I'm here.
So maybe about what, 7 after? Is that 10 minutes? No,
it's currently, it's currently 3 minutes to the hour. So
maybe, just give me a second.
Okay, sure.
Yeah, so we can come back about 12 o'clock. Yeah, so 12:10.
12:10, okay. Good.
Yeah, 12:10 should be fine.
Okay.
Thanks a lot. Yeah.
Okay, I guess, shall we start again?
Okay, Paul, yes, let's go ahead.
Okay, right. So what I want to do in the last part of our session today is to review what we've covered the last 2 weeks and sort of hit some of the major points in review, not go over everything in detail, but so we want to think of statistics in a very general way of think of it as a measurement of uncertainty. And so when you do research in whatever field it is, we looked at ways that might affect your outcome. So there's uncertainty that we can measure. So for example, like treatment differences, individual patient variability, differences in demographics. We talked about missing data. So for example, if you're doing like a drug study, probably medication adherence would be an important thing to consider. But the one thing that we can't control is what is known as random sampling variability or uncertainty that's just due to chance. And so that's really what statistics is about, is in some way quantifying the uncertainty in our research. And so the key idea here is that when we do research, we draw a sample from a population of interest. The sample could be random, or maybe it's not random, but the question is the sample representative of the population, or is there variability that in the research sample that isn't true of the population? And so we talked about most of the statistics that we talk about are from the frequentist perspective, because that's what you find in the literature for the most part. But we talked about from the frequentist standpoint, then probability is a long-run frequency of random events over repeated sampling. From the Bayesian perspective, it's an index of confidence that an investigator has about the occurrence of an event. And even though there's sort of similar there, that there is a difference in the way that Bayesian statistics are calculated and interpreted. And so I gave this example from the frequentist standpoint of drawing a large number or an infinite number of random samples from a population, and that we could calculate the mean of each sample, the standard error, and then lower and upper bounds of a confidence interval. And for the most part, researchers look at the 95% confidence interval, which is related to plus or minus 2 standard deviations in the normal distribution. And so then when we make a statistical decision from the frequentist standpoint, our decision to reject the null hypothesis or fail to reject is based on a probability of making a wrong decision, assuming the null hypothesis is true. And so we talked about 2 types of errors that we can make. A type 1 error, the alpha error, or this is the p-value that you'll see in studies, is the probability of rejecting the null hypothesis when it's true, or Another way of putting that, we reject the null hypothesis when we shouldn't have. And then a type 2 error, which is called the beta error, is the probability of failing to reject the null hypothesis when the null hypothesis is in fact true or is false. In other words, we fail to reject the null hypothesis, but we should have rejected it. And so we talked then about p-values, the alpha error rate. It's the level that we select beforehand, before we do our study of rejecting the null hypothesis. And it's on a scale, it's as a probability from 0 to 1. So this is the level that you set for rejecting the null hypothesis, and we consider the alpha error more of a serious error than the type 2 error. So that's we want to set it low, small or low. So typically, it's the common level that you see is less than 0.05, but that's arbitrary. It could be set at something else, 0.01. And so when we have a p-value that, say, is less than our cutoff that we want to look at, say 0.05, then we reject the null hypothesis. If it's greater than 0.05, we fail to reject the null hypothesis. In Bayesian analysis, it's a sort of different approach. We have a prior belief about our event or our condition or diagnosis or whatever outcome that we're looking at. We then do research to gather data that is new information, and then based on our new information, we revise our prior belief with a what is known as the posterior belief, or that's our updated belief about what's true or what's not true. And so I gave an example of this from a study that compared 3 different drugs related to epilepsy. And we saw that they found no difference between the 3 drug groups as far as the probability of reducing seizures. And so their results and their illustration of this in their graph in figure 2 here showed that in terms of the probability distribution they look almost the same for all three groups. And remember that we did this by sampling from theoretical distributions. In this case, it was the binomial distribution, because it was either their outcome was either a yes or no. So they concluded that there was no difference. Now, if this had been the case, if there actually had been a difference, then their figure would have looked like this, where the difference that they were looking at was 65% success versus 50% success. And so had there actually been a difference between one of the drugs versus the other 2, then our illustration would have looked like this, where at the 97.5 with 97.5% confidence, then we would have had just 2.5% in our alternative distribution overlapping with the null distributions. And so that's the way that Bayesian's approach hypothesis testing is looking at a probability that the null hypothesis, or that the alternative hypothesis, is true or not. And so the intervals that are calculated in Bayesian and frequentist perspectives has a different interpretation. So in Bayesian statistics, we call it a credible interval. In the frequentist, it's called a confidence interval. And in the Bayesian interpretation, that means that when we calculate our 95% confidence interval, that means that there's a 95% probability that the interval includes the population parameter or the difference that we're interested in. From the frequentist perspective, a confidence interval means that over repeated sampling, the interval will include the population parameter 95% of the time. So most of the statistics that you see in published studies are from the frequentist perspective, although we're beginning to see more Bayesian statistics because there's an advantage to Bayesian statistics when we have a more complicated kind of research design or research question. So then we talked about, as far as statistical methods, this from the frequentist perspective, parametric statistics or non-parametric statistics. From parametric statistics, we're assuming that there's some theoretical distribution underlying our data in our test statistics. Non-parametric, we make no assumptions about these distributions. So this sort of summarized the parametric study or methods that we looked at, primarily linear regression, where our model was the outcome as a function of constant plus our regression coefficient beta times our independent variable or our predictor variable. And so when we look at linear regression, whether it's simple or whether it's multi-variable, that our outcome or our result is a rate of change. In other words, for every increase in X, our independent variable, every unit increase, whatever that unit is, the regression coefficient beta indicates the change in our outcome or our dependent variable. And then we just looked at logistic regression, where we are modeling the logit or the log odds. Our outcome is either yes or no, it's positive, negative, it's a dichotomous outcome. We have the same sort of regression equation, but now we can get an expected probability of our outcome of interest, whichever one we're interested in. And our logistic regression equation is modeling the log odds. And so the result that we get from logistic regression is an odds ratio. In other words, the odds of the event for one of the outcomes versus the odds of the other possible outcome. And then we didn't spend too much time on it, but survival analysis, although some survival analyses are parametric, we make some assumption about the distribution of the survival function. The Cox proportional hazard that had an example of doesn't make an assumption about the baseline hazard rate or survival function. But the result that we get from doing survival analysis is the hazard ratio. That is the hazard being the probability of surviving up to a certain time divided by the hazard of another group or another value of a continuous outcome. And so that's kind of analogous to an odds ratio, but it has a different interpretation where we're looking at hazard rates. So those are the primary models, regression models that we have looked at. And then as far as non-parametric statistics, those were statistics where we make no assumption about the distribution of the outcome variable. And we didn't go into any detail on these, but these are some of the non-parametric tests that you'll find in either in the literature or if you take a statistics course that discusses non-parametrics. These are common non-parametric statistics. And then we looked at non-parametric, truly non-parametric statistics, the bootstrap and the jackknife, and did, I believe, some practice examples where for the bootstrap, what we do is we randomly select an observation from the sample data, and then we replace that and then draw another sample and so on. And over a large number of bootstrap replicates, then we can estimate a test statistic like a mean or a standard deviation or confidence intervals. And then the jackknife was the leave out one way of calculating a statistic or a confidence interval. I want to talk a little bit about multiplicity, which we haven't mentioned yet, but what is meant by multiplicity is the idea of making a large number of hypothesis tests, or in other words, we do a large number of hypothesis testing. And the problem with this is that what it does is it inflates the alpha error rate, because the way that hypothesis testing is defined, that if you do enough statistical tests, you're going to find significance just by chance. In other words, even the p-value, even if the p-value is 0.05, because you've done, say 10 or 20 or 30 different tests, that could have occurred just by chance. Because remember, that's what our alpha and beta error rates are telling us is whether or not we found the result just by chance. And so where you often see this is in tables that are presented in the literature or research studies that are published, where they have these tables with a large number of variables and associated with each variable. If they're comparing, say, two different groups, an intervention group and a control group, there'll be a p-value next to each variable. And so what they're doing is they're basically, if they have a large number of these, the alpha error rate is being inflated. So if you do, for example, 10 tests and you think your alpha error rate is 0.05, it's actually about 10 times that. So you're going to be rejecting the null hypothesis actually at the 0.5 rate. So an example I have here from our HCMR study is that we looked at differences in some of the demographic and comorbidity variables by genetic mutation, sarcomere mutation, either positive or negative. And so what we did is we did a correction, what's known as a Bonefront correction for multiplicity. And so we had 9 different tests that we were doing in this table. So the way that we adjusted for the overinflation or the type 1 error rate is you just divide the normal alpha error rate, which usually is 0.05. So in this case, we went to test at the 0.05 level. So we divided 0.05 by the number of tests we were doing, which is 9 in this case. And so what that means is that for any one variable to be declared statistically significant, the p-value had to be less than 0.0055, which is 0.05 divided by 9. And so we gave both the unadjusted p-value and the adjusted p-value, and you can see that for the most part, they are pretty much the same in this case, because if our unadjusted p-value is very, very small, then even if you make an adjustment, it's still going to be very, very small. And then you can see here for a couple that weren't statistically significant. Obviously, if you make an adjustment, they're not going to be statistically significant either. So that's just a little bit about the concept of multiplicity. One way of sort of avoiding that, if you have a table that you wanted to show differences, say between two groups or maybe more than two groups, rather than doing hypothesis testing, is to calculate what is known as standardized differences. And so we can do standardized differences of means or proportions. So for means, it's just the difference in, say, two means divided by the standard deviation of the difference of two means. And that's just the variance in group 1 plus the variance in group 2 divided by 2, and then we take the square root of that to get the standard, basically the standard error of the difference. And then the same thing for proportions, the same concept. Take the difference into two proportions and just divide by the variances, the average variances, just like we did for means. The variance of a proportion is the proportion times 1 minus the proportion. So in this case, the variance for proportion 1 is just P1 times 1 minus P1, and same thing for proportion number 2. And so if you calculate standardized difference, we're not doing hypothesis testing, but it gives us an indication of whether there's a difference between, say, two groups that we might be interested in. And this is particularly useful when you have a table, usually like your table 1 in your reporting your results, where, say, you want to compare the two groups with respect to demographic variables, age, sex, so on, and or some comorbidities, the proportion who are in each group who are diabetic, have hypertension, and so on. And so the idea here is that when we calculate the standardized difference, we get a measure of the non-overlap in the distributions. So obviously, if there's a difference, if there's no difference, we get a standardized difference of 0. In other words, both means or both proportions are equal. Then the distributions are completely overlapping. And then as the standardized difference increases or it decreases, this can be negative depending on which way we subtract our means or our proportions, then the percent of non-overlap becomes greater, and this is illustrated in the figure here by the non-overlap in the two groups. And so I've given an example here of why it's in some cases better to present the standardized difference rather than p-values. And I sort of, showed this with picking extremes here. So for example, if we're looking at age and we have group 1 has an age of 64.7, the other one is 64.1, that's not really that much of a difference, but our N is so large that the p-value is 0.02, which tells us that it's statistically significant. But if we calculate a standardized difference, we can see that that's really small, which gives us a better measure or a better index of the difference here. Even though it's statistically different, it's probably not really difference in a meaningful sense. Whereas if we, say, have a similar thing where we have 60.5 in one group and 64 in another group, but only 30 then our p-value is going to be non-significant. But if we calculate the standardized difference here, which is about a 4-year difference, or maybe a little less than 4 years, then we see that the standardized difference is fairly sizable, of 0.36. So that means that there's a certain amount of overlap or non-overlap in our distributions here. And then the same thing with dichotomous variables here. This is diabetes. So we have 150 in one group and 200 in the other group. The N is 3,000. So obviously that's going to be statistically significant. But if you calculate the standardized difference here, the difference between 5% and 6.7% isn't that great, or isn't that large. And whereas here we have a small n, and we have a big difference in percentages or proportions here, it's not going to be statistically significant, but calculating the standardized difference gives us the indication that there is quite a bit of difference here. There's non-overlap in these two distributions. So statistical significance, because it depends on the sample size, doesn't always give you an accurate picture of differences. So calculating the standardized differences is sometimes really helpful. So I want to end up with just kind of going through what is involved in planning and executing a research study. So as you think about the statistics that we have talked about and the different concepts related to that, it's just one part of a study, of what goes into a study. So obviously the first thing that you need to do is to develop your research question. What is it that you want to investigate? And oftentimes this is referred to as specific aims in your study that, like when you apply for grants, you have 2 or 3 or maybe more specific aims, and then you have your research questions, and maybe you state those as hypothesis, as the alternative or the null hypothesis. So that's where you really start, is what is it you want to, what issues do you want to address? And then so given that, then how are you going to design the study? What type of study design? Are you going to be able to do a randomized trial? Is it going to be data that's from hospital records or from a data registry? And then you need to decide what is the relevant data that you need to answer your question. What is the outcome? Are there demographic variables? What other covariates might you need to answer your question? And again, that depends obviously on the question and the study design. And then the data collection methods. And this is really, even though it seems like an unimportant part, it's almost the most important part, because without good data, you really don't have any, you really don't have anything to say. So making sure that your data your collection methods are adequate, that your data that you're getting is good data. And then of course you have to think about security. And then if you're doing a prospective study where you're going to follow subjects or patients over time, then you need to develop the timeline. So like, how long are you going to allow for enrollment in the study? How long are you going to follow them to determine whether the outcome occurs or not? And then the data analysis actually usually, well, I guess maybe I'm sort of biased here, but that's usually the easiest part of of doing research, of doing your study. But you do need to do data checking or data cleaning. Are there outliers? Are there out of range values? So for example, in a study I did some years ago, there was I can't remember exactly the numbers, but there was a variable where the acceptable range was say like 0.1 to 2. And there was a value in there that was over 1,000. And so my first thought is, well, okay, somebody forgot to put in a decimal point, but do I know that for sure? Well, I don't. You have to look at extreme values or values that are out of range. Is that a real value or is that just a mistake? And then so as we talked about in doing linear regressions, when we looked at the interaction, we want to do, first of all, just descriptive statistics. What actually does our data look like? If we have comparison groups, do they differ on age? Do they differ in gender and so on? And then we actually do our analysis. And again, depending on the questions we've asked and the design of our study, we'll select the appropriate statistical test to use. And then we write up the methods and results and have supporting tables and graphs that go along with our write-up, our written report. And then often these results are either, say, presented at professional meetings, or you write it up to get published. And so usually from a statistician's point of view, I usually write up the statistical methods. Obviously, I'm not the content expert, so I'm not writing the introduction or the conclusions, but from a statistical standpoint, that's usually what I'm writing for investigators, and then making the tables and graphs that would be needed to support their results and their conclusions. So I want to thank you for your time and attention the last couple of weeks. Hope that it's been profitable and at least becoming familiar with some of the statistical aspects of doing research. And I'll turn it back over to William, that we can either keep going, or do you want to take a break? And or maybe I should ask if find out if there's any questions that people want to ask at this point over anything that we've covered in the last couple of weeks.
Yeah. So Paul, there are a couple of questions in the chat.
Okay.
Yes.
Okay, so is this the first question is, should sample size based on logistic regression in that study? Oh wait, there's more than that.
Yeah. I think there's a C index. It's unfortunate they didn't indicate a slide number, and I didn't catch this. And I think the first one is the one.
Oh, right. Okay.
With the
okay, so it'd be relative risk or relative ratio or risk ratio rather than odds ratio. So that really depends on whether your study is prospective or retrospective. So the odds ratio is what you calculate in a retrospective study. If you're doing a prospective study, then you would calculate the risk ratio, which is calculated slightly different. I think I went over that, but I don't remember for sure. Okay, then how do you get a C index? So the C index is the same thing as the area under the curve of a receiver operating characteristic curve. And so in logistic regression, what you get is the, based on your regression equation that you end up with, get a predicted probability of the event. And then you compare that with the observed outcomes and see how closely they discriminate. So if a person has a high probability from the regression equation and they actually experience the event, then if that's true of more people, then you get a C index closer to 1. If they're not agreeing, then you'll get an index a C index that's closer to 0.5. And I suspect in most software packages, this can be calculated. I don't know about Python, but I would suspect that you'd be able to
yes.
to calculate the C index.
Yes, yes,
Okay.
absolutely.
Let's see. Should the sample size be based on logistic regression in the study we looked at? Well, my feeling is that it should not have. It should have been based on the survival analysis, looking at the survival curves over the 12-month period, because that's really the question that's really what's important in a time to event study. And so what they did is they just looked at whether it occurred within that 12-month period and based their sample size on that. But at least in my opinion, it should have been based on the survival analysis rather than on the logistic regression, because the survival analysis is really what you want to look at, since you have a time-dependent variable. Now, if the outcome had just been within, did they did it occur without any time element associated with it, then logistic regression would have been the appropriate statistic to look at and to base your sample size on. Let's see. Oh, okay. All right. You're welcome. So if you think of any other questions or anything that comments you'd like to make, just please feel free to email me at my MedStar email, and I'd be happy to discuss whatever it is of interest.
Thank you, Paul. And I think I got something. Let's make sure this is exactly what we are talking about. Is a coordinates index, right? Is that what we're talking about? Paul?
Oh, yeah, the concordance index.
Okay. Yeah, so then there's an example, and that's a cool thing with these free packages. They do have, once you post something on Stack Exchange. So Stack Exchange is primarily your go-to place, or even Google. You just put it in there and you get a code and basically a sample code and a solution. Yeah. So thanks a lot. So before we move into the coding part, John, do we have any preference? I think we targeted 1 hour. Now it's 48, so we have 10 minutes ahead. So do we want to take a break and come in, or do we want to start the setup and then we'll take a break and then come in and have everyone on the same page?
Yeah, if anyone wants to take kind of a bathroom break, yeah, we can allow 5 minutes for that. No more than 5 minutes.
Okay, cool. Yeah, and then we'll use 5 minutes to do the setup. So let's do that, and then we'll come back. Let's say it's 12:50. So we'll come back 5 to the 12:55. Okay, so let's see. You are sharing your screen. I don't know which screen I'm sharing. Let me stop this and I'll take this here and do a share. Okay. Now I'm going to do a share. And I'm sharing this now. Still bouncing. Okay, so which of the screens do you see? Yeah, so as which of my screens do you see, please?
Jupyter.
Oh, good. Because the thing went to the other screen. So you see this one, right?
Yes.
Good. Yeah, thanks a lot. Okay, so 1 minute and then we'll start. So for the so that we are ahead of time, just we do the same thing we do with the housekeeping. Unfortunately, I'm using a smaller font, so you may not be able to see it as well. But you go to the location where you want the file to be. So just from your file explorer, okay. It's always good. You go to the location where you want your class thing to be. So in my case, I have my class thing somewhere. Like I said, I got two things. I've got my own, and then I've got one that, so I've got personal, which is where I work from. Okay, so the personal will be out of date. And so I won't do a get code yet. But the one that will not be out of date will be the GitHub. Okay, so you go into it. You have to see this Git. You have to see this .git. You do a right mouse click. You go to more. Okay, and Git bash here. Okay, and once you have your Git bash, my screens, I don't know why I picked this dark screen. Now it's coming back to bite me. So in here, then what you can do, you do just a git code. Assuming you've already cloned your folder, you do a git code. Let me see if I can increase the font in here. The font. Yeah, I'm used to small font, so sorry for that. Let me before. Oh, not font smoking, but actually the font size. I don't see the font size here. So I've done that some before. I don't see the font size. So just bear with me. Just do a git pull, and you see it tells me it's out of date because we haven't done anything in this. This is the directory that is similar to what Nana has created. Okay, so this location here is similar. And then I go here and I'll see the file, but I'm not going to work in here. Okay, if I make a mistake and I start working in here. Let's say I go into this file, but I don't do that. But assuming I went here and added something and I saved it, and let's say I closed, then the next time I do a git pull, it's going to complain. It told me it's up to date. I should have complained. It should have said, yeah, you have something that the other side doesn't have, so you can pull it. That's normally what it should have done. And that's why you don't work in that directory. Okay, so, and then the second thing you can do is, assuming you don't want to go through Git is giving you a hard time, then what you can do then is, I have this bookmarked, and the bookmarks, let's see, oh gee, we did this with Ebel yesterday. I bookmarked the GitHub page. Now I can't find it. Let's see. I did bookmark it. Now I can't. Oh, there we go. You see it. The VADSTI, the 2020. Okay, so that's the one here. Okay, so it should come, and you have. Oh no, I think I got it the wrong one. So let me go back again. VADSTI 2020, and I want the GitHub. So the GitHub, this one. Yeah. So then what you do is you go to the 2020 because there are multiple of these. You go to the 2022 one, and in the 2022, you go here, you download the file, okay, and then I'm repeating this because I know people have gone through the struggle before. So you even here, you can just double click and open, but I always do this. You open the file, and then what you can then do is you don't have to extract all of it. You can just extract one portion. You can just extract one portion of it, or even extract just one file of it. Okay, so that is a good thing with this. So let's say I want to extract this file, then I'll just say extract and indicate where I want it to go to. Okay, so let's say I leave it here to see. So I say go for it. Then those two files will be extracted, and once you come back to the downloads, there would be and you go to that directory, you see the two files are there. So some people like it this way. They just want to just pull just the little one, which is what Git does for you. Okay, so now we've gone through the logistics. Now we can just go into the action zone. So for the action, what to do is you can go either use the Codio. If you use Codio, as usual, we are going to open the student file. Okay, the student file will be the one in your root directory. And remember, you have to be in the 3D. Don't go in the 3. You have to be in the 3D. What I mean by this is that when you go down here, don't do the 3A, go to the 3D and pick the notebook. Okay, so that is how you get in. And then you pick the 3 day 1, 2 file. Okay, that's the student file. How do I know it's a student file? It is a student file because it has this here. Alternatively, in addition to that, because the student file will have empty slots and you don't want to get stuck. So we've provided you the solution stack, which has a name in there, and it has a similar name, but instead of exercise, it's solution. Okay, so you click on that, and you have the two next to each other, so that if you go through the student and you get stuck, then you do the instructor one. For today, though, in the interest of time, we're going to run through the instructor one, and when you are home, you do that. So that is as far as Codio goes. If you are using the other one, the Jupyter, then you have a little bit of a long stretch. You have to bring up Anaconda and Jupyter Notebook. In the interest of time, I'm going to assume, and then we do have TA session. So if you don't get that, I'm going to assume that you got that, and then you learn during the TA session. But I got my Jupyter Notebook app. Okay. Primarily the way I did it is I brought my Anaconda prompt up. Okay, Anaconda prompt, and I typed Jupyter, and I CD'd to the location where. So let me go out of this and then come back in. Let me save this. It says forbidden. Okay, hopefully I didn't lose much, but let me do this because I think in the interest of time, but then we also have to make sure everyone is on track. So I did my Anaconda. Okay, I did my Anaconda, and then once I did my Anaconda, I did the Conda prompt. So Conda prompt, remember from Dr. Musa's, so Conda prompt, Anaconda prompt. Okay, so I did my Anaconda prompt. Okay, and then once I did a prompt, it gave me this, and then I went to the location where the file is. Okay, and I basically copied the location. Okay, so I copied the location, and then when I came, I put it here. I did a CD to that location, okay, 3D. I made sure the files are there, and then I start my Jupyter Notebook. Okay, and Jupyter Notebook will just bring out a terminal. Okay, and that is how I started. And then once you are in here, I don't want to mess up with all these tabs. So I want to make this its own. Okay, so that I don't have too many tabs hanging on my neck. So let's say I move this out of the way, and then I can minimize this and have access to this with only one tab, so that when I open the file, then I only have 2 tabs instead of the 100 tabs. Okay, so, and here too, you know that this is the student file, so I've made that red. And then we go back to the parent and bring back the solution file, which will be in the solution. Okay, so you open the solution and there's a solution file. Okay, so we have student file, we have solution file, and we are set to go. Just always make sure you have that. So that's what we have. Okay, so now once we are here and we don't see any questions in the chat, then we are ready to take off. So let's make sure there are no questions in the chat. Good, no questions. Okay, now let's see. So primarily we've gone through the statistics. We've gone through with Professor Paul. So the assumption is that we understand the concepts, or we'll go back and watch the video and the concepts will be clear. Our task now is, how do you move from the theory, from the broad overview, from the expert knowledge we've gotten from 2 days of class, into actually getting your hands dirty. And trust me, it doesn't come easily. It comes with patience. You know, if you're working in Excel, my idea is that start working in Python or R. In this case, you want Python because this class Python. What I mean is that instead of doing things in Excel, you can read your Excel sheet, and that's what we're going to show here. You can read your Excel sheet into Python and work on it. Okay, so this is how you read your Excel file into Python. It's just an Excel file. You read it with read Excel. You indicate the number, and then you have a data frame. And once you have that data frame, then the sky is the limit. Okay, you can do anything at all that you want. So let's say we stop this. So if I do this, I've read the data. Now I can do, I can query the data. Okay, so df.head. Okay, and sorry, you can now query the data. Okay, which means that you can actually change a lot of things. Okay, you can do a df.age or df of age. Okay, age, just like we did in Dr. Musa's class. Maybe just multiply, add 3 to that. Okay, and let's put it next to each other and do the df of age. Okay, and compare that with what we just did. df of age and df, and make the 2 into a list. The square bracket. Okay, the square brackets are what you have to look for. This is a subset. This is a subset, and you're adding 3 to the subset, and you want to display them next to each other. Okay, so there we go. I don't know what happened. I think it. Oh, I think it went down. I should do a display instead of a print. Okay, so that's where these things come handy. That you can actually display them next to each other. Okay, or just find out how you display them next to that. Now, when I did this, the first one came first, and then the second one, because it couldn't fit on the screen, so the second one followed. And you can see clearly that the first number, which was 22, has now become a 23. Same index. Okay, and then from here, you can do all your manipulations that you do in Excel and write back into Excel. And that is how you move your computation from Excel to Python. Okay, you can do a whole lot of things in here. Okay, so for today, let's see what we have. So what we did yesterday was that, just so that we have, in case we have new people, or we have anyone who is who struggle with it a little bit. In Python, unlike Excel, all the computations are loaded. Once you open Excel, you have all access to all the computations or the computation libraries. In Python and other languages, you don't. You have to load. They give you basic libraries, and then you have to load extra libraries. Okay, so for this class, these are the libraries that will be you should have in your computer. We said that we don't want to reinstall it, so there's an exit here because it takes time to install. If you haven't done that, then you have to stop this, run this, and then once it works, you bring it back, because it takes a lot of time for this to run. And I don't want to accidentally hit a button. The exit says when you start running and you get here, don't proceed, just end it. So if I run this, I'm going to get installing and nothing else would happen. So let's say, assuming I put something in here, installing, let's say done. Let's say we say done here. Okay, done installing required packages. If I run this, let's say 2 of 2, okay, and let's say we go up and do this 1 of 1. You'll see that with the exit, when I run this, I'm just going to get 1 of 1. 2 will never be displayed because exit will block that. Okay, cool. So that now we are all set. And then we have to load some packages in your computer, depending on how you have it set up. You're going to get a warning message from time to time. I have it set up so that you can see the warning message. I intentionally made this way so you can see the warning message. Now, as you go down, I know your screen is small. So your screen real estate is small. Mine is small as well. So we give you a link to how to go to where you came from. Okay, so you can go here and you can go back. I go down here and I can go back. Okay, now let's look at the warm-up exercises. The warm-up exercises require some packages being loaded, and you just run that import. You see this time the error didn't come. And then before you do anything in Python, in fact, the Python, the headache of any language is what it can take. We call this the data types. If you master the data types, the sky is the limit. Just master the data types and then pick the data type that will do the best job. So the data types think of them as tools. Okay, so if you have a pen and you want to put a pen on the wall, you may not have to use a hammer, right? You may have to use something like that. If you have a nail, then use a hammer. Okay, that's what this is doing. So these data types take up room, they take up space in your memory. If all you're doing is just a number like x2, then it doesn't make sense for you to put it in a data frame. A data frame takes up more room than this integer data type. And if you want to, if you have a data that looks like Excel, then of course you can put 3 people in one room, right? It's going to be really crowded in there. So you move them into a room that make them feel comfortable. In that analog or analogy, you move a data frame. You take Excel and put it in a data frame. Excel files have columns, and data frames are designed for that. Each of these things gives you methods. They give you functions that you can apply on the database. On the object that you created. So if I use a pandas data frame, then I'm going to get methods that allow me to do things like things that are aware, pandas aware. Okay, so now let's run this and I'll show you what I mean. And Dr. Musa went through this, so I'm not going to duplicate effort. I just want you to see this, that the square brackets are, this is a list, okay? A tuple looks like a list, but it's open prime. And then one thing you'll be seeing very often is this, the dictionary and data frames. You're going to see them a lot because there's a key value. And the beautiful thing with the key value is you can think of them as allowing you to actually search through things quicker. Okay, so key value, instead of using the index, I can say, look for William's room and William will be there. if I don't know William's room and I just know that there's someone called William, I'll be able to find him. Without that, then I have to know William's room specifically. I have to know that William is in 6099 or something, 6399. Okay, so that's why you have to know this. And the printing is a way of you communicating your output to the outside. Okay, so you have to know the 3 different ways of printing. One way of printing is putting this double quote and then listing and then putting this percent. Okay, so the percent says I'm done indicating my print format. Whatever follows is the variable. Okay, so I'm done telling you how I want you to print it. And you're going to use these things, you place them anywhere you see the percent. Okay, so that's what is happening here. I have 1%, 2%, and 3% in the code. So I better have 3 items after the percent. This percent is different from these. That's why this percent is in purple. Okay, if you're not seeing it well, see that this percent is in purple. Okay, that says that's a formatter. Okay, it says I have a print string and I have a print string that contains a format, and I'm going to supply the values I want you to print. So if I hit this, supposing I make, let's run this. See, this is giving me a 3. So if I change this and make it 10, then I'm going to get that. Okay, this is a string, so it's going to print that S3. So if I make it S311, it's a string. Okay, so it will just come in there. And then the type is just the type of what it is. Okay, and always, if I see things that are too much, I don't struggle with it. I take it in smaller chunks because I can do that, right? I'll just do a plus here and stick it in here and see what it does. Okay, so when I combine all 3, then I'm going to get X11 has a value and it's of type that. Okay, so just take note. That's one way of doing the print. Another way of doing the print is you can actually, so this and this goes in. This is what I like. I like this type. This other way of print where you mix up what you are printing with what is being printed. So you see this parenthesis goes all the way here. And then the things that I want to print are in there and I separate them by quote. So I'm going to say this, I'm going to say that, I'm going to say equal, and then whatever it is equal, this should be in your environment. This should be a variable because it's not in the quote. Okay, so the things in quotes are literal and things outside the quote are going to be evaluated. So if I hit this, I'm going to get the same thing. Okay, and then the third way, which is the way I normally do it, is this one here. I like it because it's new to me, and I like seeing new things. Okay, so you see, this is a format. Okay, this tells me that whatever is coming in here is just a format. Okay, it's a format. That's what the F is doing. And then I can have my literal as is, but where the thing has to be printed, you use this curly bracket thing. Okay, and you indicate the variable and use it, separate the variable with a colon. It's more like the key value. Okay, so I'm saying X3 that I have created, I want you to print it in this form. The same way, this type thing that when I type, it gives me a float. I want you to just type it. There's no, you see, there's no format to it. So it's just going to bring it up. So when I do this, I have that. And I demarcate my stuff. So you have 3 ways of printing, and that's all this is doing. This is just a recall. It just putting you in a state where the rest of the code will make sense. Okay, any questions? Okay, so no questions. Oh, okay, couldn't find bash. If you can't find bash, that means if you're not able to find bash, that means you don't have the Linux type tools in your system, because all this is doing is primarily doing something like you run in a terminal, you running things in the terminal. Let's see here. Yeah, so if you can find it, then you would have to use the exclamation. Okay, so primarily, if you're not able to find it, some people will do because your system might not have been set up. Mine is a little complicated system, but what you can then do is you can do an exclamation, and you have to do it one at a time. Okay, so you take all these guys, you take out, you just put bang, bang, and you take this thing out. Okay, I'm sorry, you comment this so that it doesn't error. Okay, so primarily your thing is going to look like, it's going to look just like mine, but it's going to look like this. Okay, and I'll just take these guys out. Okay, and if I hit that, it should. No record. Oh, sorry. I don't have a pseudo. If you encode your pseudo, I'm not encode you, I'm on my system, so I don't need a pseudo. And then do that, and it will install. So please, that's a good catch. Just take out the bash and take out the pseudo and replace all the pseudos with exclamation. Exclamation says, get me into the system and just run it. Okay, and you get something like that. Okay, so no questions, right? And if you're having problems, I would say don't struggle. Come back to the good. Yeah, come back to the TA session and we'll be able to address that. Difference between a list and a tuple, this comes from Professor Musa's class. So if you look at Musa's class, the video will tell you, but I'm going to answer that. One is you cannot change it. Okay, a list I can change. So let's say I take these two guys. Oh, sorry, Control Z, Control C. I do a plus. I go down here, and I have X3 and X6. So let's try and do something. Let's say X5 of 1 equal William. Okay. Let's say William. Okay. And if we run that, it will not complain. It will work. You see, it worked. Okay. So now, let's see what will happen if we do the same to this guy. Control C and Control V. If I do the same to X6, and let's block the X5. Okay, let's block this guy and block this guy so that we see. You see that you can't do that. So a tuple you cannot change. And so if you are doing something like you are designing an application and you don't want people to, you are working with 3 or 4 people and you give them let's say you supply them data and you want to make sure that they use the data, then maybe you want to put the data in a tuple. Or if you don't want your data to be chained downstream, then you leave it in a tuple. A tuple says, this is fixed. This is what you're going to get. You're going to use it downstream. And let's say you have something, you can change it if you want. Okay, so that's one thing that you have to know. Okay, so that's a good question. Okay, so now let's keep going. Python is good. It will tell you. It will tell you that tuple doesn't have. You trying to use a method on an object, it will tell you the object doesn't have that method. Okay, sure. So now we've done all that. We don't have any questions. Let's go straight in. We have 30 minutes. Let's rush. Yesterday we went through the first task. Okay, it's just EDA. Play with it. Primarily, what it is here is that you have data sitting somewhere. You have Python, and you want to get data into Python. That's all we did yesterday. How do you do that? You can do that by creating the data, okay, like that, creating the data, or you can read the data. Okay, you can read the data from a file, which is what we did somewhere here in one of the examples, like here. Yeah, you can actually read the file. Okay, and that works. The other thing is you can get the data from a package that's or a library provided in Python. Okay, and one of the libraries that has data is the Seaborn. The reason it has data is because it's a graphical library, and so they have to give you an example. And so the best way to give an example is to provide data with the example. Okay, so that we are sure that the output they provide will match your output. Okay, so Seaborn has that. Okay, it has that. It has other data sets too. And the way to get that data is by saying Seaborn load, SB load data set. SB is the alias we gave to Seaborn when we were importing. Okay, so we can say load. So if I was importing from, let's say, NumPy, and assuming NumPy has a data, then I'll say np dot load data set in the name of the data set. Okay, so that's what this is doing. And once we run this, we're going to get, we did this yesterday, that at times you can look for, we do have libraries that allows you to look at the data without writing any program. One of it is what we saw in here, detail. Detail gives you that. And then there was another one that I couldn't get to work on Codio, and that one is Explorers. Something is one of the Explorers. Yes, it's Pandas Profile Explorer. It's really very cool. So when you go home, try and get it to run. And I provided you a link here. If you go there, you will see. So let's say you go down here. Okay, so Control C. You go down here. And you'll see, in case you don't get it to work, you see what it does. Okay, so you get all these things for free. Just like using, what's the name of this package? Like R Shiny, and oh, there's another one that allows you to explore data. So detail it gives you that. And the other one also gives you a nice way of looking at the data, making sure that the data is nicely skewed, basically having an insight of the data. As Professor Paul indicated, you have to know your data. Okay, you really have to have an insight of the data, and this provides that. Pandas Profile is one that people use very often, and that gives you a whole lot of tools as well. Okay, so it gives you all these nice, cool tools that tells you that, hey, this data is skewed left, skewed right. You can do a whole lot of nice things in that. Okay, you can do a plot. This tells me my data is all over the place. Okay, and then they have another one called SweetViz. SweetViz also gives you a dashboard type, and it tells you how to install and how gives you an example of how to run it. Okay, and there's a whole lot. So the link I provided, and one or two of it also provides you the code. Once you do it, they'll say, hey, this is the code that creates that. So it gives you an added tool that you can go back and utilize. So yeah, so the solutions sheet, please take a look at it. It has a lot of, all the links provided are links that I find very, very useful. Okay, so that takes us through here, and we go to the next phase. I think I did block this. Okay, so the reason I blocked it is because I wanted to make sure that I don't get locked out. Okay, so you would have to open that, take a look at the reference and do as it says. We saw this yesterday. Okay, and you can go in and describe your data and do all sorts of things to the data. Okay, you can see that you get nice code for free primarily. Okay, you get a nice set of code for free. Okay, cool. So that takes us through the data exploratory data analysis, which is really very cool. You need to know your data before you start doing anything to the data. Okay, and make use of this class so that you can test things out. And make sure that it works, and so you don't, in case the code is too big, take portions and put it in an empty cell And if you want to delete, you delete and you go on. Okay, cool. So now task 505, we read the data. Okay, so we're going to read the data, and we've read the data. And I wanted you to see the difference between the print and the display. So let's make it so that we can actually see the difference between the print and display, because depending on which one you use, you're going to get a different output. Okay, oh, sorry, let's see this. Display head, oh, dot head, comma, my dot, my thing. So that's the print. The print gives you that. And let's look at what display would do. I use the head so that it doesn't go all over the place. And the open parent and close parent, the square bracket, take big note of that. Okay, take a big note of that. I'm going to separate this so that you see that. Okay, the difference between the square bracket and the open parent is, if you are defining the data, one is a list and one is a set. If you have an object and you say a dot, then you're referring to a method. Okay, and a method is a function, and the function will be open parent, close parent, because it can take argument. Okay, so I'm saying give me 2 here and give me, let's say, 4 here. Now let's run that and see what will happen. And equal. Okay, so you see, I like display better than print, because display gives me something that makes it easy to my eye, especially if I move this to like a 12 and I move this to 14. I mean, like 12 and make this a 14, then you see the big difference between display and print. More so if you have a lot of columns, then this makes it easy. Okay, so that's what this part is saying. So read a little tiny text that are there, because they are there for a reason. Okay, they are there for a reason. Okay, so now let's make it everyone gets 1, 1. Okay, so we've gone through that. We went through this, and if you have a lot of text and you don't want to actually delete this, but you want the text to go away, you see, unlike other IDs, that you don't have an X yet, so you start with this. A way to block the text without you deleting your code is to comment it. Then when you rerun, the text will go on. So the text is gone away. Okay, cool. So we've done that. And then the fifth portion is just reading the data so that we can do what Professor Paul took us through. There are 2 data sets. Take note. One is the data XLS, and one is that's more like the cholesterol, and one is the sex and the other data set. Now, when you read the data, you will see that you always have to inspect the data. Okay, if you don't get into trouble. Because if you look at this slide that Professor Paul gave us yesterday, you will see that in his slide, the variables have different names. So the variable, the H variable, has a lowercase h. Okay, and Python, like any other packages, are case sensitive. Okay, so they are case sensitive, which means that if a name has an uppercase, you cannot replace it with a lowercase. It has to be an uppercase. Okay, so let's say we bring Paul's, I think Linux, exactly, because most of these languages are written in Linux, okay, or Unix, and Unix is case sensitive. Yeah, exactly. So that is the reason you have to be careful of that. Otherwise, you're going to get into trouble. Okay, you're going to get into trouble. So if you go down here, you see that Paul has weight and weight, but then in his computation, he has it like that. Okay, he has it like that. So if I want to mimic Paul's computation, then I have to be mindful of what these the names are, and I'll show you how to rename them. Okay, so always display and take a look at the data before you start coding anything. Okay, now here we go to slide 19. If you may recall, what Paul was doing on slide 19 is he was doing something like I think the slide 19 might be on the day 2 slide. Okay, it may be on the day 2 slide. Okay, so what this is saying, in the interest of time, what this is saying here is that, so this is one of the PowerPoint, and this is the other PowerPoint. Let me see my time. Oh, wow, let's keep going. So this is saying, hey, you know what? I can create a table and find the recall. Remember on slide 19, there was something like the specificity and the recall. That's how you compute it. Once you have been able to compute a true value and a predicted value, this is how you compute the recall. You say the true and the predicted, and the position of the position label is 0, means that it's a row. Okay, so I'm comparing row by row, 0, 0. So I'm comparing the 0, the true was a 0 and the predicted was a 0. So that's a perfect. The true was 1 and the predicted is 0. That's not good. Okay, so that's what it's doing. It's doing item-wise comparison. Okay, so once I run this, I get a recall. So this is just showing you how those values were computed on Paul's slide. Okay, and if I can get to Paul's slide here, I think on slide 19, that might be the other one. I think that might be this one here somewhere. Okay, so just take note. That's all we're doing. We're trying to get what Paul has on his thing. This might be a slightly labeled. So just search for specificity through Paul's notes, and you see that it's there. And this shows you how to do it. Okay, now slide 15, and I'll give you an example. So if in case my example is not very good, I let you know that you can find a better example here. Okay, so you have to look at your data and you do something called the confusion matrix. So assuming you've gotten your prediction and your true value all set up, how do you produce a confusion matrix? So confusion matrix is saying it's basically giving you that thing with the true recall and the specificity. It's giving you that in a more pictorial view. And I added numbers here so that it will match what Paul has on his slide. But this is how it's computed. There's a library you get it from, confusion matrix, straightforward. A confusion matrix means you need a true and the predicted. I basically am assuming that through the course, we would be able to have computed, let's say, the regression or the logistic regression estimate. And so we know how to get the true values. Once you have the true value and you have the predicted value, this is how you do the confusion matrix. Okay, you load your library and you primarily compute the confusion matrix, and you compute the and then you print it. In this case, I computed I'm using the confusion plot matrix method that comes from this library, and I'm just basically printing it. I mean, I'm displaying it, and that's primarily what it will do. So there's a first case where I'm printing it, so it's printing. If you expect a plot to come and the plot is not coming, there's one thing that you do. You have to do the inline. You have to force an inline view of. You have to ask Python to display the plot inline. Okay, so Control F. I'm sorry. Inline. Okay, just do an inline. Okay, I don't have the inline here, but you do an inline. So you go down here, and Professor Musa also has that. Okay, and you say, hey, Python, how do I plot inline? Okay, and that will give you that. Okay, so Google. Okay, and you say Python plot inline. Okay, I'm sure you are this because you would. There we go. And as you go down, you will see that there will be a way to do that inline. Someone would have responded. There we go. Yeah. See, so you just take that. If you take your time and read, and we come back here. Remember before the plot wasn't showing. So all we're going to do is we're going to stick this in here and force an inline view. And there we go. So you see this. I mean, you encounter some of these things, and knowledge exchange is a way to go. Okay. Because here I expected that this has to plot, and it wasn't plotting. So then you have to go Google and you get it. Okay, so that's that. That takes us through day one. I've taken my time. We have 15 minutes. Day two, I'm going to speed through. Any questions? Okay, now day two, we have a lot. Day two, all that's going to happen here is that we've taken our time. We've gone through day one. We know the fundamentals. Now we're just going to get what Paul has on his slides. Okay, so if you are here, you click this and it takes you there. So for day two, and then if you want to go back to your objective, as usual, it takes you there. Okay, so we go back there. In day two, we're going to accomplish all these tasks. Okay, all these tasks. I tell you which slides they are on. I tell you primarily what we are trying to achieve. Okay, so just take your time and go through it. Okay, so here, what we are going to do here is, remember, on slide 9, Paul was computing some ordinary least square estimate for the cholesterol. And then he had multiple models. We're not going to go through the model, we're going to see how to fit those models. To fit those models, you have to be mindful of the data. You are going to use a method. The method expects data in a certain form. And so you have to present the data to the method in that specific form. Okay, so once you read your data, you have to set up your X and the Y. Okay, your X and the Y. And your X and the Y, primarily, this is your X. Sorry, this is your Y. The Y is normally just one variable. And the X could be 2, could be 3, could be just 1. So this is my X. If you set it up this way, then the sky is the limit. Because then all you have to do is keep adding stuff. Be mindful of the square brackets. Okay, the square brackets makes the big difference. Okay, because this is a series and this is a series, but you have multiple items in the series. So then that's why you have, so just be mindful of this. Okay, this thing can bite you. Okay, so basically, how are you mindful of that? I always print and view at it, take a view at it, okay, to make sure that I'm getting the right thing. Hence, in Python, most of the methods expect them to be standing in a table form. That way, you can simply add stuff to it. Okay, so Y is it's a model, it's a linear model dependent on X. If I have X1, X2, X3, then I'm going to get more like a matrix. Okay, so that's why things have to stand upright. Okay, so now my data is fine. If my data is fine, then I just have to go in and run my model. Okay, so I'm going to use a different model here. Okay, I'm going to use a different method for that. You can either use the linear model or you can use this stats model API. Okay, and I'll show you how to do both. First thing you do is tell me what you're trying to achieve and set up your thing so that you can achieve that. I have X here just to let you know that I have different versions of the X's. I can have a Y as a linear regression on just H, and that's how you do that. Okay, and then with scikit-learn, the way you do that is you are going to define a regression object, you fit, okay, and then you pull your statistics from it, and this is how you pull your statistics from it. And then in the case of the stars model, that's much easier. Okay, you fit. Okay, so you fit, and then you can predict, and then you just print. Now, when I run this is how it looks like. And this should match Paul's output. The f-test, the adjusted R squared. I think if I move this a little bit here to the right, we should see that. Okay, you see that it fits. And these values should match what Paul has on Paul's screen. Okay, since Paul went through this, I'm not going to waste my time trying to be an expert here. I'm just showing you how you can create what Paul has. If this is too much, the way to go, as I said, take just a few of it after you've run, and that's a beautiful thing with Python. If once you've run it, you don't have to start from the top again. You can just pick portion. You can just pick portions of it and just go with it. So I can just say, hey, you know what? I want to see what this does. And then you open it up, you put it in here, and you run, and you're going to get it. It's a linear regression object. Okay, so that's the beautiful thing with Python, that I can take, once I've run that cell, I can take portions of that and run them and see what and get my output. Okay, so just note 3 things. It's, you have to find a way, 3 or 4 things. The first thing to do is you have to get your libraries. You have to get your data, define your X and your Y. Then, so that's my Y, okay? The X has double square bracket, okay? And the Y has just 1. Y is always 1 square bracket. There are cases where Y can be multiple, but for this, Y is always 1. And then once you have this, the sky then becomes the limit. You define an object, you fit, and then if you have to predict, then you predict. If you don't have to predict, then you pull your intercept. To pull the intercepts, this how you pull the intercept. Depending on the IDE that you are using, with this IDE, the web-based IDE, I couldn't get it to pop things up. Okay. In other fonts, now here I've made it so it looks very complicated, but what you can do is you can just take the prints out and then see how this is. Okay, so this is primarily what we're trying to achieve here. Okay, and the thing with Python is if I have 2 items like that, and I try to print, it prints only the last one because it's using just 1 output buffer. So to get the other guy, you have to put a print. That's why you have a print. I put prints around, okay, like that, and now you have two items. Otherwise, the previous one will be the print output for the previous one will overwrite the other guy. So what I mean by this is, without a print, you won't get 1 output like that. Okay, cool. So that's what we've done. For the other IDE, we have 10 minutes. So let me do this quickly, and then the rest, you just go through and do your stuff. Now we have another IDE here. What this one does for me, though, is that this one, it's this VS Code, it looks just like the other, what we saw. Now, the beautiful thing with this, you see this, so that in case you are trying to decide on what other things to use, you see you have that thing here, just like you have in Jupyter. So I can run that, okay, just like, you know, okay, I can run that, and then I can inspect the variables, okay, I can inspect the variables. Since we don't have time here, let me not take you in here. We'll look at this during the QA session, but you will be able to inspect your variables. So as you look for, as you learn Python, look for IDEs that will make your life easy. Okay, one of it is VS Code, and then we have PyCharm, and we have the other ones. Okay, so let's go back in here, and then we go quickly. Okay, now we've done the first one. We go to slide 12. It's always read what this is trying to achieve, read what, and then go to the slide and take a look at it so that it will sync, and then run it. So this is a case where if I don't do this, okay, so see what I'm doing here. You see my age and the sex are all lowercase. So what this guy is doing is allowing me to rename it, okay, and that's what this is doing. Okay, so we've gone through that. And then in case you don't get that exploratory data viewer to work, then you have to actually do the running yourself. You have to run, create things yourself. This is one way of visualizing your data, okay? You visualize it by taking the data. In this case, I want to group by and aggregate by mean and then plot, and do a bar plot, okay? So let's say I do it like that. The first time I do this, I was getting something very small. So I did it like that. I was getting something like that. I'm like, no, what, I can't see this. You Google around, and then you're like, how do I make my plot large? Or look at Dr. Musa's video. One way of doing that is by adding this fixed size, and then you'll get a much bigger plot. Okay, and this shows me clearly that the things, it gives me an idea of how things are. So this is the age being plotted against It's the age being plotted against cholesterol weight and PT, right? So it gives you a good idea how things stand. Okay, cool. So that's the data exploratory. Now 7.15. What this is doing is trying to implement the output on slide 12. This is a case where, if you remember, during the last lecture, Prof was saying you create dummy variables, and you create one for male and female, and this is how you do that. So I'm saying that, hey, take the data frame, create a column in there, or a variable in there called dummy gender for male, and the dummy gender for male is based on the male. Okay, if it's 0, then call it male. If it's otherwise, call it female. Okay, so that takes the sex and turns it into a dummy variable in terms of female, of male, and in terms of female. And in the same with the drag, I can make a 0 drag B and 1 drag A. And here you have to look at the code book. In Prof's notes, he had it there on slide 27 or slide 12. You see something like that, okay? And this is a 0 and a 1. Okay, cool. So that's how you recode your data. And then we keep going. Slide 13, we have 5 minutes to the time. Slide 13, just think about it and see how it's doing. Prof was trying to create more like a table by sex and drag, okay? And this is how you create that. And when you come down here, the computation of the standard deviation in the mean table, that's also on that slide, if you remember, and this is how you create it, okay? So just take note of that. Now when you go to slide 9, the slide 9 fit in the regression model, okay? So fit in the regression model, I'll give you a clear example here. You reading your data. You can also use a formula. Remember in the previous one, we were using X and Y. The cool thing with this here is that you can actually take the formula as it is and just write it. And then once you have the formula, you put it in the OLS model, okay? And you say the formula equal formula. So I'm running formula 1. I do my fit. Remember, you define the model, you fit, and you summarize. Okay, so if I run this, I'm going to get an output that looks like what Prof had. Some people like this because it looks easy on the eye. Okay, so I'm showing you that. Now let's go to the next one. This doesn't have anything implied, shows you how to look at your data. This gives you more examples on the regression, okay? And this also gives you more examples because the regression and the logistic regression, I think, are the things that you'll be encountering very often. The same thing here, okay? And then this is the assignment that we were supposed to do. We did one part of it, and yesterday, and this, you do the second part of it. The main thing is how to do your computation. Okay, you were supposed to do this by hand yesterday, but I don't think when we did a breakout, it went very well. So I decided to do it for you. Okay, and LN would be undefined, and you have to just Google around and find out how it is defined. And then once you get it, you'll be able to fit it. Okay, so that takes us through slide 12. And I think so that we don't run out of time, we'll stop here. The rest of it is like that. Please take your time, go through it. There are references, and in the bottom, just look through it. And if you have any questions, there'll be office hours today and Saturday. Last week, I missed it. I was called to the office, so I couldn't make it, but this week we'll be there. Thank you very much, and I'll pass you over to Nana so that we get time to do the survey. Oh, sorry, to John, so that we do the survey and the closing remark. Okay, John, so I think we are at the end of it. We don't have any questions, and we have all the materials. So please go ahead, run it, break things up, and anywhere there's data, provide the data. Okay, if it's not provided by Prof. Okay, John.
Yeah, thank you again. Thank you, Professor Scrum and William. We thank you so much for 2 weeks of excellent presentation on statistics and Python with all the examples. And thank you also, all of you, for participation. You want to show your appreciation to Paul and William, you can do so in the chat area, just show your appreciation. We'll meet again next week, and then we'll continue with some of the statistics. We'll be looking at data exploration and visualization. So we'll see you all here again next week. And again, don't forget to sign the attendance sheet, and also please complete the survey. Your feedback is very important to us. So thank you again for coming, and then we'll see you same time next week. William, would there be office hour TA sessions over the weekend?
Yes, so there'll be one posted. Check the Slack. Stacy would put something in the Slack, so please check the Slack. And the email, I think email will announce if there will be one today, but there will be a location somewhere in the TA session, like TA office hours. There'll be something here, like something similar like that.
Okay, so again, always go to the Slack for any updates or any information regarding the program, including TA sessions. So thank you again. If you have any questions, you can ask. If you don't have any questions, have a great weekend, everyone.
And the sign up, please, and the survey. I think there'll be a survey. Stacy, you want to just give us a quick rundown of what has to be done before everyone takes off? I think, okay. So if you need anything, you can't get answers to it, please reach out to Stacy, Nana, John, myself, or even put it in Slack. Thank you very much. And email will also work. And email. Yeah.